Welcome to AI Paper Podcasts, the show where we distill the latest in AI research and engineering, really cutting through the noise to bring you the core insights. Today, we're diving deep into a challenge that, it keeps a lot of AI researchers and ML engineers up at night. It's the black box problem with large language models. You feed these incredibly powerful models data, they generate really impressive text, but then you're often left asking, why? Why did it say that?
Exactly. Especially when we're talking about models trained on literally trillions of tokens. Trying to understand their behavior, it really feels like finding a specific grain of sand on every beach in the world. It's just that massive.
It really is. And that's where our focus today comes in, OLMoTrace. Okay, so for a quick, maybe 1-minute summary of this groundbreaking work, here's what you really need to know. OLMoTrace is this open source system developed by the Allen Institute for AI and some university partners, and it does something truly revolutionary. It traces verbatim segments of an LLM's output, like direct quotes, straight back to the exact documents in its massive, multi-trillion token training data.
And it does this in real time.
In real time, that's the kicker. Its core innovation uses an extended infinigram system. Think of it as a really advanced way of indexing huge amounts of text by pre-sorting all the text suffixes.
Right, which makes searching incredibly fast.
Exactly. It achieves this incredible speed and scale, something that honestly was previously thought computationally intractable, just too big, too slow.
Yeah, completely out of reach.
So why is this a game changer for you, our technical listeners? Well, it offers unprecedented transparency. It enables powerful new ways to fact-check outputs, investigate those seemingly created expressions, understand mathematical reasoning, and even spot potential hallucinations.
Which ultimately helps us build more trustworthy and, crucially, more understandable AI.
Okay, so with that powerful overview, let's really get into the weeds of how OLMoTrace actually pulls this off. Our mission today is to pull back the curtain on this complex system, explore its ingenious engineering, and talk about the real-world implications for understanding the models we all rely on.
Yeah, and it's fascinating because the problem OLMoTrace is tackling is it's colossal.
Yeah.
Modern language models, they're trained on these truly enormous text corpora. We are talking trillions of tokens.
Billions, yeah.
And critically, a lot of this data is often proprietary. It's not public. You can't just go look at it easily.
So you have this incredibly intelligent model, performs amazing feats, but until now, there was no real way to see its brain or its memory, so to speak, when it generated something specific.
Precisely. And as these LLMs get adopted in more high-stakes situations like medicine, finance, law, knowing why they generate a specific response becomes absolutely critical. You need that accountability.
Yeah.
And the traditional behavior tracing methods, things like influence functions, they just haven't scaled. They're too computationally heavy, too demanding for these multi-trillion token environments. They break down. They become intractable.
So that real-time tracing on these huge data sets, that's where the breakthrough really lies. The speed is just revolutionary. How did they crack that fundamental challenge?
Well, the core idea for the speed is actually quite brilliant in its simplicity, conceptually at least. Exact matches can be located incredibly quickly if you pre-sort all the possible suffixes of the text lexicographically, like sorting words in a dictionary, but for every possible ending of every sentence.
Okay.
And this is where that infinigram system comes into play. As you mentioned, it's this advanced indexing engine that really powers the ability to search at this unprecedented scale.
And when we talk scale, we're not just throwing around big numbers loosely. Can you give us some specifics? Like, how much data are we really talking about for just one model?
Okay, let's take a concrete example. The OLMo 232B Instruct model. It's one of the flagship open language models from AI2. OLMoTrace matches against its entire training data, all of it.
Wow.
And that includes 3.2 billion documents, billion with a B.
Okay.
And a staggering 4.6 trillion Llama 2 tokens. That spans across its pre-training, its mid-training, and its post-training data sets.
4.6 trillion tokens. It's hard to even conceptualize that amount of text.
It really is. It's vastly more than any single human could ever read, in multiple lifetimes.
That really underscores why it's been such a black box. The sheer volume makes direct inspection just impossible. So, okay, let's break down the journey then. A response gets generated by the LLM. How does OLMoTrace process it to find its origin? You mentioned a clever 5-step inference pipeline. It's not just an instant lookup. Walk us through that.
Certainly. So the first step in this pipeline is finding what the paper calls maximal matching spans. This is where the system identifies all the longest possible segments or spans of the LLM's output that appear verbatim, word for word, somewhere in that massive training data.
So it's looking for exact copies, right? Not just similar ideas or paraphrased content, direct quotes, essentially.
Exactly, direct verbatim copies. And there are some strict criteria for these spans. They obviously have to exist in the training data. They need to be self-contained, meaning no periods or new lines cutting them off mid-span unless it's at the very end, and no incomplete words.
Okay.
And, importantly, they have to be maximal. That means a span isn't counted if it's just part of an even longer matching span found in the data.
Got it. Find the longest possible exact matches.
Right. Now, this initial step is actually the most compute-intensive part of the whole process. But OLMoTrace uses a fast parallel algorithm that leans heavily on that infinitogram suffix array index we talked about. This clever approach reduces the computational complexity from something like OL squared, which is terrible for long sequences, down to OL log n. That's a huge leap in efficiency, making it feasible.
That efficiency gain is critical.
Yeah.
Okay, so now you've got potentially a lot of these maximal matching spans. How does OLMoTrace avoid just overwhelming the user? That brings us to step 2, filtering for interesting spans. Why is that filtering so crucial?
Yeah, exactly. You could have tons of matches, especially for common phrases. The goal isn't data overload, it's actionable insight. You can't just present every single match.
Right.
So OLMoTrace filters these down. It keeps only a small percentage the paper mentions, typically keeping K spans, where K is about 5% of the total length of the response in tokens, 0.05 ito-PL. And crucially, it keeps the ones with the smallest span unigram probability.
Smallest unigram probability. Okay, unpack that. Why that specific metric? Why not just the longest spans?
That's a great question. They found that simply picking the longest spans wasn't always the most informative. A lower unigram probability indicates a span that is usually both relatively long and contains less common, more unique tokens. Think of it like finding a sequence of words that's statistically less likely to occur by chance.
Ah, okay.
This helps surface phrases that are genuinely distinctive and more likely to offer real insight into the model's specific training sources rather than just, common filler words or very frequent phrases strung together. It's vital for keeping the user interface clear and focused.
That makes perfect sense. You want the signal, not the noise. So you've isolated these unique, interesting spans. What happens next to actually connect them back to the source documents?
Right. So for each of these interesting spans, we move into steps 3 and 4. This involves retrieving and then merging documents and spans. First, OLMoTrace retrieves up to 10 document snippets from the training data that contain that specific interesting span. Just the relevant context, not necessarily the whole document initially.
Up to 10 snippets per span.
Yeah.
Okay.
Then, for clarity in the user interface and just to tidy things up, it performs 2 merging steps. It merges overlapping spans that were found in the LLM's output text, and it combines snippets that actually came from the same original training document.
So it groups related information together visually.
Exactly. Prevents clutter, makes it easier to see the connections.
The whole pipeline sounds really robust. And I imagine the visual output, the UI, is where this really comes alive for a user, right? How does that final presentation work?
Yes, absolutely. Step 5 is where the user experience is key. Re-ranking and coloring documents by relevance. To prioritize the most useful information, the retrieved documents are ranked using a BM25 score.
BM25, that's a standard search ranking algorithm, right?
It is. For those maybe less familiar, BM25 is common in search engines. It helps figure out how relevant a document is to a query, looking at things like term frequency and how unique terms are across documents. And here, the clever part is the query they use for this BM25 score. It's the concatenation, basically sticking together your original prompt and the LLM's generated response.
Ah, so it considers the whole conversation context for relevance.
Precisely. This ensures the retrieved documents aren't just lexically similar to a small part of the output, but are actually contextually relevant to the interaction you just had with the model.
And then it uses colors.
Right. Visual cues are super important. Documents get bucketed into high, medium, and low relevance categories. This is reflected by a color-coded sidebar in the UI. And here's maybe the neatest trick. The highlights on the LLM's output text itself also take on colors. The color of a highlighted span corresponds to the maximum relevance score of any of the training documents that contain that span.
No, that's smart. So you instantly see which parts of the response are strongly tied to the most relevant training data hits.
Exactly. It's a very intuitive way to grasp the strength of the connection at a glance. really well thought out from a usability perspective.
Okay, we've talked through the logical pipeline, but the core engineering feat, the thing that makes this possible, is how incredibly fast it is when dealing with trillions of tokens. What's the behind-the-scenes magic enabling that real-time performance?
Yeah, the speed is definitely where a lot of the magic lies. It comes down to some very smart engineering choices centered around that infinigram engine. As we mentioned, it indexes the training data using suffix arrays. But here's the key. Instead of trying to load these absolutely massive index files entirely into RAM, which would be impractical, maybe even impossible, for trillion token datasets on reasonable hardware, they store them on low latency SSD disks, solid state drives.
Right, so they're accessing from disk, but super fast disk. That avoids the RAM bottleneck. That's a huge difference.
It's a critical design choice for scalability. And of course, parallelization plays a massive role too.
I was just about to ask that.
Absolutely. The algorithm for finding those matching spans performs a single find query for each suffix of the LLM's output text. And these queries are processed in parallel across multiple shards or sections of the index, likely spread across multiple machines or cores.
Distributed processing. Makes sense.
Yeah, this distributed approach is key to getting the speed down, and the result of pretty impressive latency figures. The paper states their production system hosted on Google Cloud with, get this, 64 vCPUs, 256 gigs of RAM, and 40 terabytes of SSDs averages only 4.46 seconds to trace a typical 458 token LLM response.
Under 5 seconds for that scale, that's genuinely real time for practical use.
It provides a really smooth experience for a technical user doing analysis. Right? It doesn't feel like you're waiting forever.
That's incredible. Okay, so this sounds incredibly powerful. Let's shift gears a bit. How can AI researchers and ML engineers, our listeners actually use OLMoTrace in their day-to-day work? Let's dive into some practical applications that are now possible.
Right, let's talk use cases. One of the most direct and obvious applications is fact-checking LLM outputs. Imagine a scenario. An LLM states something as a fact. If OLMoTrace highlights that statement, it means it was found verbatim in the training data.
Okay.
For example, the paper mentions the LLM stating the Space Needle was built for the 1962 World's Fair. OLMoTrace can highlight that exact phrase and show you the specific training document, often even with a URL pointing to the original web page where it likely came from.
That's huge for verification. It helps you immediately judge the potential reliability of the source. You can see if the model is just repeating something it read, maybe something out of context, or maybe from an unreliable source like some random web page. It clarifies the provenance instantly.
Precisely. It doesn't guarantee the fact is true, but it shows you where the model likely got that exact string of words.
Right. What about creativity?
Yeah, another fascinating use case is tracing what appear to be creative expressions. LLMs can generate text that seems genuinely novel or, imaginative.
Like maybe writing a story in the style of a famous author, like J.R.R. Tolkien.
Exactly that kind of thing. The paper gives an example where an OLMo model generates a story in Tolkien style and uses the phrase, "I'm going on an adventure." Seems fitting, maybe even creative in context.
Yeah, very Bilbo Baggins.
Right. But what OLMoTrace reveals is that this phrase gets highlighted, and it's traced back not to Tolkien's original works necessarily, but to a piece of fan fiction about hobbits that happened to be in the training data.
So it exposes the underlying sources. It shows how models might be sort of stitching together creativity from patterns they've seen, rather than generating something wholly new.
Exactly. It gives you insight into the compositional nature of LLM creativity. It's pulling from its vast memory banks.
That's a really powerful insight into how these things actually work. Okay, what about something more analytical, like understanding their math capabilities? Do they genuinely reason mathematically, or is it more like memorization?
OLMoTrace offers a valuable window into that question too. Let's say an LLM correctly solves a pretty complex math problem. The paper uses an example of a combinatorics problem from a competition, the AME 2024 exam. The model might show the calculation, maybe something like binom 2, 210, looks like it did the math.
Right.
But OLMoTrace might reveal that that exact calculation string appears verbatim in its post-training dataset, perhaps from a website discussing solutions to that exam.
Okay, so it might not be reasoning from first principles in that instance, but rather recalling a stored solution or at least a specific calculation path it encountered during training.
Exactly. It offers crucial evidence to help distinguish between apparent reasoning and potential memorization. And this raises really important questions for us as researchers about how we define and, more importantly, how we evaluate AI capabilities, especially in domains like math and logic. It pushes us to design better benchmarks that test true generalization, not just recall.
That distinction is key. And it seems like this could open doors beyond just understanding specific outputs. Could it help with things like, say, bias detection or understanding generalization more broadly?
Absolutely, I think so. The ability to trace an output back to specific training data segments gives us a completely new tool for auditing models. If a model consistently generates biased content, OLMoTrace could potentially help pinpoint if that bias stems from specific, maybe heavily repeated or influential, problematic patterns within the training data itself.
So you could potentially identify source material contributing to bias.
Potentially, yes. It's not a magic bullet, but it's another investigative avenue. Similarly, for generalization versus memorization, this is a fundamental question in ML. OLMoTrace can provide evidence. Is the model applying learned principles to new situations? Or is it mainly retrieving and slightly adapting specific instances it saw in its massive data set? Seeing the verbatim matches helps explore that distinction.
This sounds incredibly versatile, but to make sure we're crystal clear, it's probably important to clarify what OLMoTrace isn't. For instance, it sounds a bit like retrieval-augmented generation (RG) systems, because both retrieve documents, but they're different, right? What's the key distinction?
Yeah, that's a really important point to make. They are fundamentally different. While both involve retrieving documents, OLMoTrace is strictly post hoc. It analyzes the LLM's output after the generation is complete. Its sole purpose is to show the connection between that finished output and the training data.
Okay, analysis only.
Right. RG systems, on the other hand, like the ones powering maybe Bing Chat or Perplexity AI, they retrieve documents before or during the generation process. They use that retrieved information to condition the model, to improve the quality or factual grounding of the output as it's being generated. OLMoTrace doesn't intervene in generation at all.
Got it. So OLMoTrace is an analysis tool, not a generation enhancement tool. And it's also not quite like a traditional web search engine either.
That's correct. A traditional search engine, like Google, might optimize its results. It might drop results for efficiency, or maybe even for business reasons, like profitability. It doesn't necessarily show you everything it found.
True.
OLMoTrace, however, aims to faithfully retrieve all exact matches within the scope of the LLM's training data. It provides a complete picture within the limits of verbatim matching, which is crucial for scientific transparency and thorough analysis.
Complete and faithful retrieval within its scope makes sense. And it's also distinct from older techniques like influence functions. We touched on this, but maybe reiterate the difference.
Yes, worth reiterating. Older methods like influence functions try to identify influential training examples by looking at gradient information. How much changing a specific training example would affect the model's output or loss.
Right, mathematically tracing influence.
Yeah. But as we discussed earlier, those methods are just computationally intractable for today's trillion-token datasets. The cost and complexity are just too high. OLMoTrace takes a completely different, much more scalable approach, direct lexical overlap. It operates under the reasonable heuristic that if the model repeats something verbatim, that source text was likely influential in some way. It's a different philosophy, optimized for massive scale.
Okay, that clarifies the distinctions.
Yeah.
Now, given all this power and this unprecedented level of transparency, there must be some important limitations or, let's say, considerations to keep firmly in mind, especially for our technical audience using this tool.
Absolutely. There are critical caveats. The first, and perhaps most important, is that finding a verbatim match does not imply causality.
Okay, say more about that.
The retrieved documents show lexical overlap. The same sequence of words exists. But you shouldn't automatically interpret that as meaning the document caused the LLM to produce that output, or that the document serves as supporting evidence or a citation for a factual claim the LLM made.
That's a crucial nuance. Just because the model saw it somewhere doesn't automatically mean that specific instance is why it said it now, or that the source itself is reliable or even correct. It's correlation, not necessarily causation.
Exactly right. It shows a connection, a potential source, but not necessarily a direct cause or validation. That requires further investigation.
Good point. What else?
Another critical consideration stems directly from the transparency itself. This level of tracing means OLMoTrace could inadvertently surface or expose problematic content directly from the training data. We're talking potentially copyrighted material, personally identifiable information, PII, that might have slipped through data cleaning, or toxic language, hate speech, misinformation, basically anything bad that might exist in a huge web scrape.
So the transparency cuts both ways. It reveals the good and potentially the bad lurking in the training data.
Precisely. It's an incredibly powerful tool for understanding, But with that power comes the responsibility to be aware of and careful about the nature of the information it might expose from that underlying data. Users need to handle that responsibly.
That makes sense. So bringing this all together, what does OLMoTrace really mean for the future of LLMs and how we, as researchers and developers, interact with them?
I think OLMoTrace represents a truly significant leap forward in peeling back the layers of these often opaque, massive language models. By providing this real-time, granular tracing of outputs right back to the specific locations in their colossal training datasets, it empowers technical users like you listening with a level of visibility we simply haven't had before.
Yeah.
It provides insights that were previously just unattainable, allowing us to ask and begin to answer entirely new questions about why LLMs behave the way they do.
And that leads perfectly into our final provocative thought for you, our listeners. Knowing that you can now trace an LLM's memory, it's a verbatim recall, to such a deep and specific level within trillions of tokens, what new questions does this capability provoke for your own research or your development work? How might you leverage this kind of transparency to build models that are more robust, more reliable, perhaps more fair, or maybe even more genuinely creative and verifiable ways? Something to think about. That's all for this deep dive into OLMoTrace on AI Paper Podcasts. Thank you for joining us.